A planet's albedo, or surface reflectivity, dictates how much starlight it absorbs. Ice sheets reflect energy back into space, creating delicate feedback loops that can stabilize or destabilize global climates rapidly. For decades, humanity has gazed upward, asking a fundamental question. Are we truly alone in the universe? Or is another living Earth hiding among the endless expanse of distant star systems? Dr. Elena Vance stands before a massive holographic display inside her laboratory, tracking the faint rhythmic signals of newly discovered exoplanets orbiting faraway stars across our vast, whispering galaxy. What actually makes a world habitable? It is not just about finding water. It requires a delicate cosmic alchemy of distance, atmosphere, chemistry, and time working in absolute unison. First, location is everything. Planets must reside within the circumstellar habitable zone, famously known as the Goldilocks Zone, where it is neither too hot nor too cold for liquid water. Step too close to the host star, and any surface water instantly boils away into a runaway greenhouse nightmare, turning a promising world into a scorching, sterile planetary desert. Venturing too far out into the frozen abyss yields a very different fate. Here, water freezes solid into permanent glaciers, locking worlds into eternal winters under faint starlight. Yet distance alone tells only half the story. The type of star a planet orbits dictates its survival. Not all suns are created equal, and many possess violent tempers. Red dwarfs are the most common stars in our galaxy, yet their violent flares can blast away nearby planetary atmospheres, stripping worlds of the very air required for life. To endure stellar hostility, a planet needs an invisible shield. A powerful planetary magnetic field deflects deadly solar winds, keeping the delicate atmosphere anchored to the surface below. This magnetic defense system is powered by the planet's interior. A churning, molten outer core of liquid iron acts as a colossal geodynamo, generating invisible protective forces. When a small world cools too quickly, its core solidifies and the magnetic field collapses. Mars suffered this exact catastrophe billions of years ago, transforming into a dry wasteland. Mass also dictates destiny. If a world is too small, its weak gravity cannot hold onto volatile gases. If it is too massive, it becomes a crushing gas giant. Earth hits the sweet spot. With just the right mass, it retains a rich, pressure-stable atmosphere that nurtures weather systems, stabilizes temperatures, and distributes vital moisture globally. An atmosphere is more than a blanket. It is a chemical engine. The exact ratio of nitrogen, oxygen, and carbon dioxide determines whether a planet can support complex biology. Greenhouse gases are often vilified, yet in moderation they are essential. Without them, Earth would freeze solid into an ice ball, dropping temperatures far below zero. Too much of a good thing, however, leads to catastrophe. Venus experienced a runaway greenhouse effect, trapping volcanic heat until surface temperatures melted lead. Maintaining this balance requires a planetary thermostat. Earth relies on a slow, majestic carbon cycle, scrubbing carbon from the air through rock weathering and volcanic release. This thermostat is driven by plate tectonics. Continents drifting slowly across a molten mantle recycle carbon dioxide, preventing the planet from freezing or overheating. Many rocky worlds lack active plate tectonics. Without this geological heartbeat, carbon builds up in the atmosphere or gets trapped permanently underground, killing long-term stability. Where did all Earth's water come from? Ancient cosmic impacts delivered vast reserves of ice-rich comets and asteroids during the turbulent formation of the early solar system. Once water pooled on the surface, it formed global oceans. These vast fluid expanses act as planetary shock absorbers, moderating extreme temperature swings between day and night. Earth also enjoys a unique stabilizer, our oversized moon. Its gravitational pull locks our axial tilt in place, preventing violent, chaotic climate swings over millennia. Without a large moon to steady it, a planet's rotational axis can wobble wildly. One millennium could bring tropical heat, followed by the next bringing polar ice sheets. Our solar system also features cosmic bodyguards. Massive gas giants like Jupiter use their immense gravity to sweep up or deflect deadly comets away from the inner rocky worlds. Location within the galaxy matters just as much. The galactic habitable zone avoids the dangerous radiation-soaked core, while steering clear of the outer edges lacking heavy elements. Too close to the galactic core, frequent supernova explosions would blast nearby planetary systems with sterilizing gamma radiation, destroying nascent biospheres before life can begin. Finding these ideal worlds requires extraordinary technology. Because planets are small and faint against the blinding glare of their host stars, direct imaging is nearly impossible. Instead, astronomers look for shadows. The transit method detects the microscopic dip in starlight as an exoplanet crosses directly in front of its host star. Another technique measures the stellar wobble. As a massive planet orbits, its gravitational tug makes the host star dance back and forth in a subtle, measurable rhythm. NASA's Kepler Space Telescope revolutionized this search, staring at a single patch of sky for years and revealing that planets outnumber the stars in our galaxy. Today, the James Webb Space Telescope takes us further, peering directly into the atmospheres of alien worlds using infrared vision to decode their hidden chemistry. When starlight filters through an exoplanet's atmosphere during transit, specific elements leave chemical fingerprints, absorbing exact wavelengths of light like a cosmic barcode. One of the most exciting discoveries is TRAPPIST-1, an ultra-cool dwarf star hosting 7 rocky Earth-sized planets packed tightly into a compact, harmonious orbital dance. Within the TRAPPIST-1 system, at least 3 planets reside comfortably inside the habitable zone, raising tantalizing questions about the potential for alien biospheres. Yet living around a red dwarf comes with a catch. Due to intense gravitational forces, these planets are often tidally locked, keeping one side in eternal daylight and the other in darkness. Life might still thrive in the temperate twilight zone, a narrow ring circling the planet where perpetual sunset creates stable weather patterns and mild, livable temperatures. Even closer to home lies Proxima Centauri b, our nearest exoplanet neighbor orbiting the closest star system, sparking intense dreams of future interstellar exploration. While red dwarfs are common, astrobiologists also hunt for Earth twins orbiting sun-like G-type stars, seeking the familiar warmth of a yellow sun and familiar seasonal rhythms. Finding a habitable world is only step 1. The true holy grail is detecting biosignatures, chemical fingerprints left behind by living organisms altering a planet's atmosphere. Free oxygen is a powerful indicator. Because oxygen is highly reactive and binds easily with other elements, its persistent presence in an atmosphere requires constant replenishment by life. Methane offers another clue. When paired with oxygen, it creates chemical disequilibrium. Without biological sources constantly replenishing it, methane breaks down quickly in sunlight. Nature can trick us, however. Volcanic activity or intense UV radiation can generate oxygen without any biology, forcing scientists to search for complex chemical combinations. Beyond organic biosignatures, researchers also listen for technosignatures, artificial radio waves, industrial atmospheric pollutants, or city lights illuminating the dark side of a planet. Projects like Breakthrough. Listen use giant radio observatories to scan millions of star systems, searching for intentional transmissions from an advanced technological civilization. The next generation of telescopes will go even further. Concepts like the Habitable Worlds Observatory aim to take direct photographs of Earth-like planets orbiting distant stars. Direct imaging requires extreme engineering. Because host stars are billions of times brighter than their planets, telescopes must use advanced starshades to block the blinding glare. When we finally capture a direct image of an Earth twin, it will appear as nothing more than a pale blue pixel, yet that tiny speck will change human history forever. Water, once thought rare, turns out to be abundant throughout the cosmos. Icy moons in our own outer solar system harbor vast subsurface oceans beneath miles of frozen shell. Moons like Europa and Enceladus prove that habitability does not strictly require sunlight. Tidal heating from giant planets can keep underground oceans warm and chemically active. On Earth, life thrives in the most extreme environments: boiling hydrothermal vents, acidic lakes, and frozen polar ice. If life starts here, it could flourish anywhere. Conversely, the rare Earth hypothesis argues that while simple microbial life might be common, the precise cocktail of conditions required for complex intelligence is vanishingly rare. From stellar stability to plate tectonics, asteroid shields to oversized moons, our existence is the result of a monumental cosmic gamble that paid off against impossible odds. Yet humanity's innate curiosity refuses to accept isolation. Every telescope built and every signal scanned represents our relentless drive to look beyond our horizon. We stand on the precipice of a profound revolution in human history. Within our lifetimes, we may finally answer whether we share this universe with other living worlds. In the grand tapestry of space and time, Earth is precious and fragile. Searching for another home reminds us of the urgent need to protect the one we already have. The instruments grow sharper, the data grows richer, and the distant targets come slowly into focus. The universe is whispering its secrets to anyone willing to listen. From the molten cores of terrestrial worlds to the icy outer edges of planetary systems, the search for life drives our scientific evolution and defines our cosmic destiny. We are the cosmos waking up and studying itself. As we venture further into the dark, we carry the hopes of a pale blue dot, searching for its long-lost celestial twins. The answers are out there, waiting among the stars. Every discovery brings us one step closer to finding another Earth and redefining our place in the universe. What distant exoplanet excites you the most? Subscribe and join our journey through the cosmos as we continue exploring the greatest mysteries of space and planetary science.